So indeed, as Catherine said, I'm coming from more the systems and control community. And with systems and control, what we do is system theory, and we try to estimate models from measured signals. And this is highly related with machine learning. Yes. So hence the title of my presentation. So transfer function estimation by using these kernel-based approaches coming from machine learning. And I'll show you how you can combine the insights that we have from systems theory, from engineering, to enhance the prior knowledge that you will give to kernel-based techniques. So it will be about transfer function estimation. Of course, you all know what a transfer function is from the system theoretic perspective. A transfer function gives a lot of information about a system. Take, for instance, a mass spring damper system. You can think of a force applied to the mass. You will see the movements as a result. So the transfer function will describe how the force is translating into a displacement. And just by looking at the transfer function, you can say a lot about the system. For instance, where is the resonance? What is the damping of this system? Another example is an electrochemical impedance spectroscopy. Here the transfer function is typically an impedance of a metal. And the impedance of a metal typically follows a sequence of poles and zeros on the real axis, giving, you know, these. Should I use this one? Yeah, doesn't really matter. Yeah, then you won't see online, of course. So if I use the arrow, it might be easier. Well, you just see on the transfer function that you have this sequence of poles and zeros. When it decreases, you just had a pole. When it increases again, you have a zero, and so on. Okay, so what I want to do is I want to estimate transfer functions based on data, and I will use for that some Bayesian techniques. Bayesian techniques, so I'll introduce that by making a small comparison between what I call classical regression on the one hand and kernel methods on the other hand. So for classical regression, if I introduce this calligraphic M, that would be the model set. And for classical regression, what you typically have is that a model is either in the model set or it's outside of the model set, right? Yes, so that's what I show here. In white, you are outside of the model set. In blue, you are inside the model set. When you look at Bayesian techniques, instead of having model structures which are either in or out, you have a probability of a model, right? So there you have some values which are blue, which are darker blue, which are lighter blue. So you can define a probability for each model, whether it's a good model or not, as a prior knowledge. Yes. For classical regression, the model set, if you have to determine the complexity, it will always increase in discrete steps. Yes. So if you have to determine the model complexity and you increase the model order by some number, it will always be in discrete steps. While with the Bayesian techniques, and that's what is different with it, you can tune the model complexity in a continuous way. Yes, so it could be that the prior knowledge that you give to your estimator, it varies continuously, just like you would see here. Yes. So let's just have some kind of recap of kernel-based techniques, and I'll show it just on a toy example in time series. So what do you have? You have the red dots, which are data sequences, right? And so the idea of regression in general is to find some kind of curve which connects these dots. Yeah, so you might be looking for the black curve that goes through the dots here. Yes. So how would you estimate this black curve in classical regression? You can think, for instance, of simple linear least squares, where you would say that the red dots are actually the x's equal to the true x, x0, plus some noise e, yes? And then you could, for instance, propose a model structure which would be given as a linear combination of basis functions. Yeah, so that the x hat is equal to phi times rho, where phi is a matrix of basis functions. Yes, and the rho would be the parameters then. Yeah. So what would be the estimate there? Well, the estimate would be the parameters rho in such a way that the difference squared between the measurements and the estimates are minimized. Yeah. So yeah, just to visualize that, we have that x hat is equal to, so x hat is a column vector, phi is a matrix with basis functions, so rho are the parameters. And we have an analytical solution to this problem, that's with the pseudo-inverse. You all know that, yeah? X hat is then given as phi times the pseudo-inverse times the measurements x. Classical linear least squares estimation. Now, if you go to kernel-based estimation, what you'll do is you will do two things. You will first increase the number of basis functions. Number of basis functions can potentially go to infinity. Yeah, you can have an infinitely wide phi matrix. The problem with that is that the problem becomes ill-posed. You will probably have an overfit, and you will not have unique solutions. So we have to deal with that, and the way we deal with it in kernel-based regression is by adding some regularization. And very typical, well, the regularization I will use here is just the sum of squares of the parameters, which is added to the cost function. Yeah, you can also express the solution of this problem analytically immediately in this way. So x hat is equal to what is written there. And well, we can for convenience call this part alpha. And if you put that onto the left-hand side, you will see that you have, so phi transpose times alpha. And then there's good news here. The good news is that by using this regularization, you obtain a solution where the infinite dimension disappears. Yeah. So this product of phi and phi transpose, if you make this product explicitly, you will see that the result is just a square matrix of the dimensions of the data. Yeah. I think you're all familiar with this. Yes, of course. You see the relationship with the least square support vector machines? Yes. Okay, so you put that into your solution. It will not always all be about this, of course. It's just to make sure that everyone is on the same pace. So I replace phi transpose in the solution by the k. And so what I have here is the matrix k, which is called a kernel. And so the point is that what I did here is I replaced the problem of finding good basis functions for the problem by finding a good kernel for the problem. Yeah, so that would be the kernel that will give a good description of the data. Yes. So you can ask yourself, so what is the point of going to kernel-based regression instead of least squares by using basis functions? And well, the question is, how do you define a good kernel? Hola. And then suddenly the connection got lost. Can you still see me?
We can see you, but not the slides.
You can see me, but not the slides. Okay, so the slides are back. So we change the problem from choosing good basis functions to choosing a good kernel. First question is, what is a valid kernel? The valid kernel can be determined by also something you know, I guess, Mercer's theorem. Mercer's theorem saying that the kernel is equal to, well, a valid kernel equal to phi transpose is, well, K is a valid kernel if this kernel is semi-positive definite and if it's symmetric. Still, this does not answer how you choose a good kernel. And to choose a good kernel, I will use another interpretation of the kernel-based regression. I will use the interpretation of what we call Gaussian processes. You've heard of that as well? Yes? No? Some? So Gaussian processes, again, the same problem. We have some data points which we want to interpolate in one way or another. We won't do it by using basis functions, but we'll do it by imposing some kind of correlation between the different samples, the subsequent samples. Yes. So we'll say that we'll define this covariance function, which will determine a correlation between samples that are next to each other. Covariance function is given here, for instance, in green and red. So this covariance function is mainly diagonal and it decays on the off-diagonal elements. Yeah. So how do you read the correlation of 2 points on this covariance? You choose, of course, 2 points, x1 and x2. How would the data point on x1 or x2 be correlated with the data point on x1? That's something that you can just immediately read from this covariance function. Yes. So at this point, x1 and x2 are fairly close to each other. If you choose an x2 which is a bit further from x1, then you can read the correlation a bit further, which is lower. Yes. So this kernel or this covariance function, it actually defines what I would call a prior distribution of the data. If you have a prior distribution, you can combine it with the data, which will give you a posterior distribution. This posterior distribution is again a complete distribution, which is given here in a gray shaded area. It forms these kinds of sausages in between each pair of data points. And so these sausages, they give the uncertainty of the model in between these two data points. Yeah. Why sausages? Well, because in this case, I assumed that these points are actually noiseless. So that's why the uncertainty goes to 0 at the data points, and then it grows again when you go in between the two data points. Yeah. So this distribution is the a posteriori distribution, can define a posterior covariance matrix for that as well. And you can determine the maximum of that posterior distribution. And that maximum of the posterior distribution is called the posteriori estimate, given here in the black line. Now, it turns out that this black line, the maximum a posteriori estimate, is mathematically exactly equal to the regularized least squares problem or solution that we had just before. But this Gaussian processes interpretation gives you an additional interpretation of what the prior covariance means, right? It gives you an interpretation in terms of covariance of correlation of data points. So this was a problem of interpolation. We can also have a look at a problem of smoothing. So in this case, I have again a data set where the data points are more closely to each other. Yes, but they are noisy. Yeah. So I add as a prior distribution, and that's something that you might not see on the slide, but so I use the same prior as before, but then on the main diagonal, I add a constant to take into account the fact that there is some noise added to it. Yes. The posterior distribution, well, it looks like that again. You have a gray band around the data points, and so that is a posteriori distribution of your model given the data and the prior. In this case, you don't have these sausages anymore. That's because we assume that we have noise. So the maximum posteriori estimate in this case will not go exactly through the data points. Yeah. So this is an example of what I would call smoothing by using kernel-based regression. So we have interpolation and smoothing. In fact, it's twice the same problem, but then with a different prior. In the first case, we didn't have noise. In the second case, we have denser data, but with noise. Yeah. One more thing about kernel-based regression, and I'll show that on an example kernel. So I'll use, for instance, this k equal to phi transpose equal to the squared exponential kernel. The squared exponential kernel is shown there on the right. And so this squared exponential kernel depends on what you'll see there on the left on the L, which is a length scale, which is a correlation length of the kernel, which is actually determining the width of these off-diagonals, the width or the speed at which the off-diagonals decrease. Yeah, so it will determine the correlation length of the final estimate. And this L is a number that you can vary in a continuous way. It's not a discrete number, you can vary it in a continuous way, which means that the model complexity in the end will also be varying in a continuous way, or variable in a continuous way. To illustrate that, so you will have continuous complexity tuning. To illustrate that, I have again an example on data sets. So the red points are the data sets, the black line is the estimate. At this point, this estimate does a lousy job. That's because on the right-hand side, you see the kernel that I've been using, and it's a kernel with a very, very wide off-diagonal. So the off-diagonals, they decrease very slowly. So that means that the estimate is going to be very, very smooth. This is an under-modeling. Yeah. I can decrease the correlation length. I can decrease that progressively. And you'll see that at some points, well, I get a better estimate. And if I let L decrease even further, well, you will get some kind of over-modeling. Yeah, so the model will try to follow the noise more. But still, the important thing here is that the tuning of the L can be done in a continuous fashion. Now I'm making L bigger again, smaller again, and I could say, well, let's stop here, just a bit earlier. That's a good model complexity. Well, so yeah, now I just did it by hand. Of course, there are some more formal criteria to determine the model complexity, but this is just to illustrate how this can work. Yeah, I will not talk about this at this point. So now I give this overview, well, this short introduction about kernel-based regression. I would like to apply that to transfer function estimation. So I will do transfer function estimation by using kernel methods, and I will do that in the frequency domain. Where in the frequency domain, well, you see that we have a few advantages there, and just because I like it. So a short recap. So an LTI system, we're going to talk about transfer functions of linear time-invariant systems. I'll denote it in this way. So U is the input, G is the impulse response, right? E is some additive noise on the output. And in the time domain, the relationship between these signals is as follows. So the output Y is equal to the impulse response convolved with the input signal U. Yeah. What about the frequency domain? Well, the frequency domain is actually easier, namely the output is equal to the multiplication of the transfer function and the input spectrum plus the spectrum of the noise. This is a very nice expression, but it's not very usable because typically when you make a measurement, well, this expression requires the data to be known from -infinity to +infinity because you need to compute the convolution. Or in the frequency domain, since you need to compute the Fourier transform, you need these data from -infinity to +infinity. If you work in a window, you will have what we call a transient contribution, transient term. Yeah? Transient term both in time domain and in the frequency domain. And then you might think, okay, so transient terms might be easier to deal with in the time domain, but I'll show you that in the frequency domain, it's not much more complicated. So let's have a look at that. So in the frequency domain, output is equal to G times U if the input signal is periodic. If the input signal is periodic and you apply a window which has the right size, so it has a right length equal to an integer number of periods, then you can show that you can replace the Fourier transform by the DFT. So Y of A is a DFT of the output spectrum or output signal windows, yes. G omega k is the transfer function evaluated at the DFT frequency k. U of k is again the DFT of the input. This is true for periodic signals. That's the advantage of using periodic signals. And you can simply say y is equal to g times u, even for windowed signals. If the system is in steady state, if you make sure that the window has the right size. Yeah. Just to visualize that, if you apply a periodic signal in the frequency domain means that you have discrete components. Yeah. The discrete components in the input u, you see these discrete little arrows. They give you discrete little arrows in the output as well. Yeah. So you just compute the transfer function at those frequencies by dividing the output DFT by the input DFT. This is not true anymore. If you're working in a windowed case, but with non-periodic signals, we'll see what happens then. Then you will have a transient term, and let's do a thought experiment to see what this transient term should be. This thought experiment is as follows. So I have a system G. The system G is excited by an input signal U, which is non-periodic. And I consider this signal U only in this time window, which is indicated by the gray rectangle. Yeah. The output will be non-periodic, of course. I only look at the output signal in the window. So that's actually what you have. You have a non-periodic excitation, you get a non-periodic response. To determine what the transient term is, I do another experiment where I use the same input signal inside the window. And outside the window, I make sure that the signal is a periodic repetition of what I have inside the window. There you go. So in the left-hand side, in red, you have inside the window the same signal as the blue signal above, but I made sure that I made it periodically repeated, such that the response is also periodic. So for the red experiment, the periodic experiment, I have the same expression as before. Y is equal to g times u. So what is the transient term? Well, the transient term is going to be the difference between the two outputs inside the window. Let's plot them on top of each other, and you see that they are related. They are related except at the beginning. If you compute the difference between the two, you get the green signal, and this green signal is exactly the transient term. What does the transient term look like? It looks like an impulse response. Actually, it's not an impulse response, it's a free response of the system. It's a response due to some initial conditions. Yeah. Since it's a free response of the system, it will be highly related to the transfer function. Actually, you can easily show, you can easily demonstrate that if you would say that G, transfer function G, is a rational form written as B divided by A, that the transient term is actually equal to another polynomial, I, but also divided by A. The transient term has the same poles, has the same denominator as the transfer function. So it's highly related to the transfer function. Yeah. So we're going to use that in the kernel-based regression approach. So again, we have our system equation, the system equation, y is equal to g times u. G might look like this, an example of a transfer function. The input spectrum can be, for instance, some kind of white noise. We also have a transient. This transient, it has a lot in common with the transfer function. Namely, it has a poles in common with the transfer function. That's why it looks like a bit like the transfer function. The zeros might be different. That's why the dip in the transient term is not there. We also have some noise, and and then the output spectrum is, of course, the sum of all these things. The whole idea now in transfer function estimation is to, by using input and output spectra, to estimate transfer function and transient term, taking into account the fact that there might be some noise. Using kernel-based regression means, and more specifically, using the interpretation of the Gaussian processes means that we presume that this transfer function is actually a realization of a stochastic process. So here you have a transfer function, realization of a stochastic process. You can think of a lot of other realizations of the stochastic process. So the problem now is to define this kernel function that we started with. That would be a good description to describe this stochastic process that is called a transfer function. How are we going to do that? So we're going to describe the transfer function as a Gaussian process. Transfer function is smooth. We already saw that, well, with the Gaussian processes, with kernel-based regression, we can easily estimate smooth function. That's nice. Transfer function is complex, consists of the real and imaginary part. Is that difficult? Well, it means that we'll have to take into account a stochastic process in 2 dimensions, namely in the real and imaginary part. Yeah. So, yes?
Question on the chat. Would you like to answer it now or at the end?
It depends on the question. What is the question?
The question is the window for the output occurring at the same time as for the input?
Yes, yes. So it's always the case that the window.
First repeat the question.
Okay, so I should repeat. The window for the output occurring. Yes, so if is the window for the output occurring at the same time as for the input? Yes. So they need to be synchronized. That's very important. If you make a measurement here of the input and the output is measured 2 hours later, the signals will not be related with each other. What about delays in system or response that should last longer than the window? So if the response lasts longer than the window, you will have a very long transient error. Yes. So typically, when you make a measurement of a system which has a long response, it's better to make a measurement, to foresee a measurement which is at least as long and preferably a few times longer than a typical time constant of the system. So if you have a very slow system like a crane where the mass is going to move, to oscillate very slowly, then you won't have enough with a measurement of a millisecond. Yeah, you won't be able to say anything about the system there. So it's important to match the length of the window with the speed of the dynamics of the system. Yes. Okay, so back to our Gaussian processes with to estimate FRFs. So we'll have a look at how we can use complex Gaussian processes as well. We'll also look at the problem of stability. Can we encode stability in the kernel of the Gaussian process? So first, yes, so that's actually what I'm going to start with. How to define a kernel for a stable system. And it's most easily to interpret that in time domain. So if you have, for instance, this impulse response, resonating impulse response, which decays exponentially with time, well, let's encode this exponential decay in the kernel. Yeah, so we define, well, it has been defined in literature a few times already now. We define the diagonal correlated kernel. The expression is given at the bottom right. And what you'll see there is that the main diagonal of this kernel, if you look at the plot, at the image, main diagonal is decreasing exponentially, right? That's the main diagonal. The off diagonals are also decreasing slowly. So the decrease of the main diagonal, which is exponential, is going to encode the stability of the system, while the off diagonals are going to encode some smoothness of the estimated impulse response function.
I also have a question.
Yes.
You said that that you would see the transfer function as a stochastic process. Do we see it somewhere here as well? Is this what you're now going to do to define it as a stochastic process, or is this not related to the kernel that you have to find?
Well, so what we're doing is we are defining the transfer function as a stochastic process, such that should I repeat the question? Okay, so the question was, do we see the transfer function as a stochastic process, and is that what I'm doing now? Yeah. So Of course, when you have a system, the system is not a stochastic thing. It's just, it has a transfer function that it has. When you're using these kernel-based regression, Gaussian processes in particular, you presume, it's a kind of abstract hypothesis, that the system that you have is a realization of this stochastic process. So you need to define a prior knowledge as a distribution, which of which the transfer function that you're going to measure is likely to have been drawn from. And that's what we're seeing here. So we're actually defining this covariance function as a prior knowledge about, in this case, first the impulse response, and then we're going to translate that to the frequency domain to work on the transfer function. Yeah. So this is a time domain kernel for the impulse response function. We go to the frequency domain. Well, so the time domain, in the time domain, we say that the impulse response function is a Gaussian process. We presume that the mean value of the Gaussian process is 0, and that the kernel is what I just showed. So the time domain kernel, it will be the DC kernel in this case. Yeah. In the frequency domain, well, we have the advantage that a linear operation on a Gaussian process remains a Gaussian process. So the transfer function, which is a Fourier transform of the impulse response, is also a Gaussian process of which you can compute the kernel simply by applying the Fourier transform to the kernel in both dimensions. I will not go very deep in that. This is just what it is. You apply two-dimensional Fourier transform, and you get the frequency domain kernel. And that's what you see here. So on the right-hand side, the frequency domain kernel. So that's a kernel that we're going to use as prior knowledge to describe the prior distribution of the transfer function to be estimated. Yeah. The kernel in time domain has two what we call hyperparameters. It is determined by the decay rate. How fast does the main diagonal decay? And how fast do the off diagonals decay? Yeah. So the first thing is the decay rate. So that's how fast the main diagonal decays. In the left-hand side now you see the DC kernel where the decay is very, very slow. Yeah, so the main diagonal is almost a constant. And in the frequency domain, this translates into a kernel which is mainly diagonal. You see that the main diagonal has a very high weight. Yeah. What does that mean? Well, it means that in the transfer function, you will have a high complexity because the correlation between the points of the transfer function will be very little correlated. So you will allow for a high complexity of the model. What happens now if I make the decay rate shorter, so the decay goes faster? It's an animation here. So the decay rate is faster, and you see what happens in the frequency domain. You see that the frequency domain kernel widens. The correlation in the frequency domain is increasing. I can play that again for you. So I start with a long decay rate, and I shorten the decay rate. And you see that in the frequency domain, the kernel becomes wider, increasing the correlation over the frequencies. By making the impulse response function shorter, I decrease the complexity of the model, right? Which translates in the frequency domain to a more smooth transfer function. If you have something short in time domain, you'll get something smooth in the frequency domain. This is how you can see that in the kernel here. Illustration. This is an estimation of a transfer function. The black line is a true transfer function, which is not known, but I show it here. The red one is the estimate of the transfer function based on simulation data from input and output. Yeah. The error is given in blue. I start with a kernel that you see on the bottom right, with a very long decay rate. Yeah, so a high complexity of the model. And you see that the estimated model is quite noisy. The error in blue is fairly high.
So is the kernel in the time domain?
So here the kernel is given in the frequency domain. So this is a DC kernel in the frequency domain. Yes. If I make the decay rate shorter, let's see what happens. You see that the complexity decreases, the estimate becomes smoother until it becomes too smooth. Yes. So again, you can find some kind of optimal value of this decay rate. And of course, in practice, I do not know what the error is, so I'm cheating here. But you can think of it as balancing the variance, which is high here, and the bias, which becomes higher at this point. So this might be a good model, right? There's also time correlation, and you can make a very similar study about that. So time correlation here on the left, time domain kernel. The correlation is fairly high at this point. And a high correlation in time domain means that the kernel, if you have a look at it on the right-hand plot, the kernel will be mainly concentrated to the low frequencies. A high correlation, smooth impulse response means a low frequency systems, a low pass system, if you want. If I change the time correlation, I make the time correlation shorter, you will see that in the frequency domain, you get more and more weight towards the higher frequencies. So the system is allowed to be more high frequent. Yeah, I can play that again. So the main diagonal on the frequency domain kernel becomes higher towards the high frequencies. Again, on simulation examples. So at this point, I impose a high time domain correlation. You see that the error in blue here is fairly high. The estimated transfer function in red is, well, it's a low frequency system, right? It's a low pass system. I decrease the time correlation. I increase the frequency domain weight towards high frequencies. And you see that the system is now allowed to be high frequency as well. So that was the idea of kernels for stable systems. This frequency domain kernel, it's actually only one part of the story. It's only the magnitude of the kernel. For transfer functions, the kernel is going to be complex because the transfer function itself is a complex stochastic variable, a complex variable. Yeah. So we'll have to look at complex Gaussian processes. I don't know how much time I still have. 15 minutes. So I'll be fairly short on that. So complex Gaussian processes. I'll start with the naive approach, saying that the probability density function of a complex Gaussian process is just the same as for a real Gaussian process, but then with the new complex covariance matrix. But then I forgot about the fact that a complex number actually consists of a real and imaginary part. And you have to take into account the correlation between these two as well. Yeah. So the second equation there is just a probability density function of a Gaussian distribution for real and imaginary parts, where you will see the covariances of the real parts, covariance of the imaginary parts, and the correlation between these two made explicit here. But then G is equal to the real part plus J times the imaginary part. So you can think of a transformation between G and the real part and the imaginary part. Yeah, so we define this matrix at the bottom there, I, Ji, I minus Ji, as, well, I call it n-1. It's typically used like that in literature. And we use a transformation in the expression in the middle. And by doing that, we're actually going from a distribution for real and imaginary towards a distribution of complex and complex conjugate. Yes. And the matrices that you see there, the KFD, that's the covariance matrix as we know it. The CFD is the covariance between the complex variable and its complex conjugate. And that's actually required to be taken into account if you want to properly describe complex Gaussian variables. We call it the gamma, the augmented covariance matrix. Yes. So concerning this C is called a relation matrix, and it's actually for transfer function related to the covariance matrix itself, because G is symmetric with respect to 0. But that's just a technical detail. So to summarize about the complex Gaussian processes, we look at the covariance between real and imaginary path, or alternatively to the complex transfer function and its complex conjugate. We define a covariance matrix which takes into account the covariance between G and its complex conjugates, which introduces the relation matrix. And so we get there at the bottom left a visual representation of this augmented covariance function. That's just the magnitude. The phase is coming right here. This is what you need to do to be complete to estimate transfer functions with complex Gaussian processes. So y is equal to g times u plus t plus e. G described with prior knowledge this kernel that we defined. T, well, since it's very closely related to the transfer function, it has the same pole, so it has the same decay rate, we'll use the same kernel. Yes. E, assume for now that the noise is uncorrelated in the frequency domain, so it consists of a diagonal matrix. U is rough. Rough in the sense that it varies rapidly over the frequency domain. Otherwise, you will not be able to distinguish G times U and T in the output spectrum. Yeah. So all of this, well, this is a sum of 3 Gaussian processes, which are, as a result gives a final Gaussian process, which is the output spectrum. The estimated G, and that's just a standard expression, the estimated G is given as a function of Y by multiplying to the left by the inverse of this covariance matrix, and then by the kernel times UDH. UD is a square matrix with the input spectrum on the main diagonal. That's just the expression. And then, well, I don't think I have to explain you how you do kernel tuning. I'll go very quickly over that. That's with optimizing the marginal likelihood. So we saw that Y is given by a Gaussian process, given by a covariance function that we just saw. This covariance function depends on some parameters theta, which are called the hyperparameters. How do we tune these hyperparameters? Well, we find those hyperparameters which increase the likelihood that this prior distribution has generated the data that we measured. You all know that, right? Okay, that's fine. So this is the expression, the logarithm of the marginal likelihood is given by what we call a data fit and a complexity penalty term. We maximize this with respect to theta. Just as a small illustration on the same simulation I had before, if you just let it run, on the top right plot, you will see the log marginal likelihood as a function of the decay rates. And if you minimize it, and I can just do that manually, I guess that this is approximately the minimum of that function, you will see that it coincides nicely with the point where bias and variance have been traded off well. If I go a bit further, the bias increases. If I go a bit more to the left, the variance increases. So the marginal likelihood in this case gave a nice result. And now some new thing. So a challenge, the lowly damped systems, and this is work done by Noël Hallemans here as well in the room. The problem with a DC kernel is that it imposes smoothness. If you have lightly damped or lowly damped systems, these systems are going to oscillate very long. And this is prior knowledge that is not explicitly encoded in the system. You could say that, well, the decay rate is very, very slow. And the smoothness is very low as well. This will induce a very high complexity in the model, right? So you will need a very complex model to be able to capture the lowly damped oscillations with a DC kernel. The results with a DC kernel, this is the error. It's fairly high. The error is fairly high, especially at the resonance frequencies. Yeah. So what we wanted to do, what Noel did, is he said, you know what, let's just assume that we have a good idea of what the resonance frequencies are and what the damping is. And we're going to enhance our kernel by introducing that as prior knowledge. We're going to say that the impulse response function also contains some terms which are lightly damped. These terms are given here. So Gn of t is equal to an exponentially decaying term times a resonating term. So you have there exponential minus alpha, and then zeta 1 cosine omega n. Omega n is then, well, let's see how I did it here. Yeah, so omega n is a resonance frequency, and alpha n will be the decay rate, which might be very slow. But if you know the decay rate and the resonance frequency in advance, you might use that as prior knowledge. Yeah, and you also have the zetas, which are the pole residues. So what we'll do here is we'll define a new kernel, a resonating kernel, which takes that into account. It looks a bit like a rank 1 kernel, but in the implementation, we said that the pole residues can still be stochastic, and so the rank will probably not be 1. Right? Okay. So we have a resonating kernel there. Question that is on your minds, and that I will just ask you now: how do you do with the hyperparameters? Right? So you're introducing quite a lot of additional hyperparameters here, namely the resonance frequencies, the pole residues, and the decay rate. Well, we have to find some kind of starting values of those. Yeah. And to do that, we will use the local rational method. Local rational method, what does it do? Well, we start again from this expression, y is equal to g times u plus the transient term, and we'll say that this g and the transient term are locally approximated by rational forms. These rational forms, so what is that? You say that g is equal to the division of a b polynomial and an a polynomial. Same for transient term. Possibly the transient term and the transfer function have the same denominator. And we express that in a local frequency band around k. And we estimate these rational forms. These rational forms will be of fairly low order, because this estimation is done in local frequency band, very small frequency band. Let me illustrate that. So we have here measured output spectra and input spectra, left and right. We'll just say for now that we have a transfer function g, which is not known, but I just show it here to make it clear. So what does the local rational method does? It defines a local frequency band. You see it left and right in the input and output spectra, gray bands. You use just that band to estimate a rational form. And the rational form is given here in red. And you just keep the central point. You throw away the rest. You do that for all frequencies. Yeah. This is how the local rational method works. The advantage of that is that since you work with a very little amount of data, in a very limited frequency band, the model complexity required to do that will be very low. So this gives you, if you work in a sliding frequency domain window, an estimate of the FRF, the transfer function, at all the frequencies that you measure. So what you estimate there is not only the transfer function as a point, but it's also a set of poles and zeros, right? And so all these poles and zeros can just be gathered together. And there we used an algorithm which is called, I'll go there. We use an algorithm which is called dbScan. dbScan standing for density-based spatial clustering of applications with noise. Basically, it's a clustering algorithm which is going to find where the clusters are of the poles. And we're going to use the centroids of these clusters as initial estimates of our resonances, of our poles. If you zoom in, you'll see that, for instance, the blue dot that we had there is, well, it's actually a cluster of a few poles with some uncertainty around it. Yeah.
There's a question.
Yes.
Does this imply that you need to know the amount of poles before that? So do you need to provide the model order to the user?
So the question is, does it mean that you need to know the amount of poles? I don't know if dbScan requires you to tell the number of clusters. Okay, so Noel just answered that you don't need to know the number of poles because the dbScan is going to tell you how many clusters are relevant here. Yeah, so this is something that can be done automatically.
How do you define then the density that you use to detect what is a cluster? That's the parameter that you have to use. So you
Let us first repeat the question. So you don't define the number of clusters in dbScan, but you have a density parameter that you have to set. And I'll give the mic to you.
So Noel will answer now. It's nice to have him in the audience.
So I choose as a density, I choose the frequency resolution. So it's the difference in frequency between two DFT lines. And when you choose that, then you can see that you can cluster them nicely, as good as you can. But indeed, this is a parameter you have to choose. And I think this is the best choice we can make for the moment. Good.
Yeah, so you base your choice on the frequency resolution of your measurements, so which depends on the measurement time that you use, so the window length, yeah, which is actually giving the resolution of the FRF. Okay, so we use that. Noel uses that and defines a new kernel, which is the sum of the DC kernel and 4 of these resonating kernels. The DC kernel is there just to make sure that whatever has not been captured by the lightly damped resonances can still be captured by something that is more generic. Yeah. As a result, so that's again the true transfer function. And I showed you here the errors for the DC kernel, for the local rational method, and for the DC plus estimated resonating poles. You see that the error, the yellow error, is clearly below all the others, possibly not much lower than the LRM at the resonance frequencies. This might still be improved, right, by maybe tuning this prior knowledge of the resonating poles. But what is more important here is that this yellow, well, the estimate corresponding to the yellow error is a continuous estimate in the frequency domain, whereas the orange estimate, the LRM, is a non-parametric estimate, which has as many points as the number of frequencies that you measure. Yes, the yellow one is an analytical function, an analytical estimate of the transfer function. Yeah, so to wrap up, what we talked about here were kernel methods applied to estimating transfer functions, and so we use it in the frequency domain. What we saw, what I discussed a bit more into details, were the transients, which appear for finite window lengths, how you can deal with that using kernel-based techniques as well. We looked at interpretations for frequency domain kernels, decay rates, time correlation. We looked at how Gaussian processes can be expressed for complex signals, complex systems with a relation matrix, and how you can include prior knowledge about the resonances obtained from LRM, the local rational method. I have here a few references. It's non-exhaustive. It's in order of appearance. There we go. And well, there's one reference that is fairly important to us at this point. You might have heard that it's so the important reference is the bottom right, is the LRM. You might have heard of the passing of Professor Rick Pintelon last month. He was a very nice person, very inspiring to all of us. And this paper that was just accepted for Automatica was probably one of the last papers that he actually proofread. So it has his quality stamp on it. That's what I wanted to talk about. Thank you very much.